Good morning, everyone. Welcome you all for the webinar related to wind engineering for long span bridges part 2. We'll be starting the session in exactly 2 minutes. During the presentation, if you have any questions, please feel free to put your questions on the Q&A box, not on the chat box. Please put your questions on the Q&A box. Thank you.
Good morning, my fellow engineers. It's a pleasure to welcome you again to another event of the IStructT in partnership with our good friends from RWDI, the world famous company that you know dealing with wind engineering and wind tunnel testing. It's our pleasure to have with us this time round Mr. K. Suresh Kumar, Dr. K. Suresh Kumar, who's Vice President of RWDI, to speak and to moderate the session, of course, our own Professor Prem Krishna, a well-known personality in wind engineering in this country. It is my pleasure to also welcome Abhilash, who's behind the scenes doing all the work for making this event happen, the second in the series. The first lecture given by Professor Suresh, by Dr. Suresh, was part 1, and today's part 2. And he will be covering topics which will be introduced by our Professor Prem Krishna. A little brief about IStructT. The IStructT is a body of engineers dealing with structural engineering. It is a well-known body in India promoting the art and science of structural engineering. A prominent thrust area of it has been to ensure that its members have the requisite technical knowledge and experience updated on a continuing basis with programs such as these. General public is benefited from IStructT since they get a safe and well-designed infrastructure provided by qualified and skilled members of the association who are continuously upgrading their skills, as I said. IStructT also prepares guidelines, commentaries to codes, explanatory handbooks for the benefit of the structural engineers. By joining the association, you will be in close proximity to the experts such as whom you see on the screen today, and committed experts having a vision of sustainable future for structural engineers. So if you're keen on structural engineering, I would advise that you become a member of IStructT. It's also my pleasure then to introduce the speakers today, the moderator today. Professor Prem Krishna is our moderator, and he will be moderating the whole session, after also introducing the speaker himself. Professor Prem Krishna did his B and ME structures from Roorkee and then went on to Imperial College in London in '64, having got his PhD in funicular suspension systems. He was thereafter at what is now IIT Roorkee, then University of Roorkee, and retired from there in 1998. He maintained close contact with that institution till 2007, and every now and again he would go off to Illinois Urbana and the Imperial College London as sabbatical or on sabbaticals and be there. In addition to being a committed teacher, he's been keenly active in R&D and very closely interacting, especially with steel structures and the industry, long span bridges and wind engineering. These three focus areas of his. Dr. Prem Krishna has a particular interest in cable roofs and bridges and was the author of Cable Suspended Roofs, published by McGraw-Hill in '78 and updated just recently in 2013. He has proof-checked a number of cable structures, bridges, roofs in India and elsewhere. And as such, his studies on cable-stayed bridges such as the Vidyasagar Setu, complete design of the footbridge at Roorkee, a pedestrian cable-stayed footbridge at Roorkee, and road bridges at Haridwar, being the first cable-stayed bridges in India, and proof-checking of a number of cable-stayed bridges in his own capacity. Our panelists include Professor Mahesh Tandon, who is yet to join. I hope he will join shortly. Everybody knows Professor Tandon. He's a professor guest professor at IIT Gandhinagar, and he's the past president of IS Shakti and managing director and owner of Tandon Consultants, a very famous consulting firm in India. He is an eminent structural engineer. Many of the structures designed by him have had acclaim in India and abroad. He is an international PE, professional engineer. His structures have been described as highly creative, futuristic, aesthetic, environmentally sensitive, and innovative. His special areas of interest also include motivating the next generation to take up civil engineering as a profession and a vocation in life. The other panelist, Dr. Lakshmi Parmeshwaran from CRRI in Delhi, holds a PhD in civil engineering from IIT Roorkee and more than 33 years of professional experience in research, teaching, and consultancy. She is the chief scientist at Bridge Engineering and Structures Division of CRRI in Delhi, professor of engineering science ACSIR. Her areas of research include wind engineering. In fact, her PhD was on the same on cable-stayed and wind engineering, cable-stayed bridges and wind engineering, wind tunnel studies on chimneys, cooling towers, microwave towers, and has designed many wind-sensitive communication structures and TV towers, etc. She has contributed to the bridge management system in CRRI, mobile bridge inspection unit, structural health monitoring of bridges, distress diagnostics and rehabilitation of bridges being her key areas. She has authored more than 120 technical papers and is a visiting scholar at Johns Hopkins University at USA. She is a recipient of the Boycast Fellowship from Department of Science and Technology, INGRC Best Paper Award, and so many other commendations from Institution of Engineers and others. She's a member of various IRC and BIS committees and significantly contributes to the drafting of various codes of practice and guidelines, including for cable-stayed bridges. In fact, the wind section of the new guideline on cable-stayed bridges is led by Professor Prem Krishna and Dr. Lakshmi, the new guidelines that will be coming out. And these talks that Suresh is giving and the other series where Dr. Lakshmi has spoken, etc., they are all adding up to the sum body of knowledge, including this talks that we recently had on this whole course that we ran on cable-stayed bridges, the wind section in those courses. All those are giving us effective information for the engineer for developing the guidelines. So with that, I would like to transfer the baton to Professor Prem Krishna to go ahead. And I might just tell you that what I'd affectionately say is he knew my father very well, and that we both are PhDs from the same alma mater of Imperial College London, and in fact know many of the professors there even today and are closely in touch with them, and that is the bond I share with our moderator. On that note, good morning all, on the seat now.
Well, thank you, Dr. Harshvardhan, for setting the ball rolling, telling us about the activities of the IAS Shakti and introducing the two of our panelists. and also for your very kind introduction of myself. The activity on long span bridges and wind engineering has seemed to pick up considerably during the last few months. And for a lot of activity that Dr. Harsh described that is going on, the guidelines in the IRC, the webinars, and the lecture series, and so on, he has been playing a very, very active and a role steering all these very, very passionately. And for that reason, perhaps he is the one out of the five that are here. The moderator, the speaker, the three panelists. He's also a panelist today. He requires the least bit of introduction. However, I would like to just, as a formality, just speak out a few lines for him. And before I do that formality, I'm very touched by his remark about the Imperial College, both of us being alumni of the Imperial College in different time windows, of course. I was there in the 60s and Harsh, I believe, in the 90s, perhaps. So Dr. Harshvardhan is a chairman and managing director of the well-known consulting firm, Construma. And as he just mentioned, a PhD from Imperial College. He is a vice president of International Association of Bridge and Structural Engineering, IABSE, Zurich. He is also a member of the technical committee of IABSE Zurich and chairman of its bulletin editorial board, member of FIB, Commission on Durability and Service Life Design. He also is a member, obviously, of the number of bodies in India, the IRC, the BIS, and the Highway Research Board, and so on. He's actively serving on the committees and helping the profession there. He has been involved in a number of landmark projects, such as the Signature Cable Stayed Bridge at Delhi, the Railcom Road Bridge at Patna, Bridge number 20 on JURL, metros, viaducts, elevated roads, arch and extradose bridges, ROBs, underpasses, and the list can go on. And apart from that, also involved in repair and rehabilitation of more than 60 numbers of bridges. So we have a very accomplished panelist here, and I'm sure when we come to the question answer session, he will give us invaluable inputs. Dr. Suresh, as has been mentioned, is today going to present to us the second part of his talk, Wind Engineering for Long Span Bridges. Part one was done some time back. In fact, if I may say so, this is third in the series of webinars on wind on bridges. The first one came from Dr. Lakshmi, an excellent presentation on short and medium span bridges. And then came Dr. Suresh Kumar with part one of wind engineering for long span bridges. Again, a very outstanding introduction to the subject. And very obviously, people wanted more. They wanted then to go to advanced issues and not just the introduction. And I think that is the sequel to that we are having part two. In fact, I might mention that he began by taking a scope which was somewhat large for a particular presentation in 1 hour, and certain topics then he decided to cut from that list. And I think, I'm sure that part three will come sooner or later, which will cover those parts which he is not taking up today. In fact, he's today going to talk on, let me see, the aeroelastic modeling and aeroelastic wind tunnel modeling, vehicle pedestrian induced vibrations, cable stability analysis. And what he is leaving out today, I think, is full-scale measurements, supplementary damping, health monitoring, and retrofitting. So those I think he is leaving out for our next exposure. And he's going to cover aeroelastic modeling, cable stability analysis, and pedestrian or vehicle-induced vibrations. Dr. Suresh is a very eminent wind engineer, one of the most experienced in this country. And he's about 30 years of experience behind him. He is the vice president and principal of the famous RWDI, Rowan, Williams, Davis, Irwin. I think that's the four names. And he was in fact responsible for setting up a new wind tunnel, the fifth wind tunnel of RWDI in Thiruvananthapuram, where he leads a group of 50 technocrats. He has, to his credit, worked on many famous structures. I might mention a few. The Burj Khalifa, the redoubtable Burj Khalifa. And at the time that this Burj was being analyzed and designed, and wind seemed to be the major issue there in design, there were very few guidelines or codes or literature that would cover the wind engineering that was required. So a lot of innovative work in wind engineering had to come to make sure that the Burj would stand up to its 864-meter height against the wind loading. The other structures, Tacoma Narrow Suspension Bridge, the Statue of Unity in Gujarat, many towers in Bombay, the International Airport Terminal 2 at Bangalore, and currently now into bridges directly, the Mumbai-Pune Missing Link Cable Stayed Bridge. So he's fully involved into bridge engineering and leading a group at Thiruvananthapuram, which is I think the only commercial outfit in this country dealing only with wind engineering. So you have in him a very, very highly accomplished wind engineer, and I'm sure we are in for a very expert lecture from him. May I now invite Dr. Suresh to kindly present his talk.
Thank you, sir. Thank you for the kind introduction. And welcome, everybody. I think there are lots of people from many parts of the world. So I'm saying good morning, good evening, as well as good night. I think I know people are from different parts of the world. I had to thank iStruct for giving an opportunity to present under their banner. And all the panelists, I have to thank them for their kindness to be here, commenting on the work. And then the team RWDI, I think there are lots of people behind these kind of webinars. So they have been working day and night to arrange these type of webinars. So I'm thankful to them as well. So just to set the tone, I just want to say that I have 59 slides in precise. And I'll be talking more on the conceptual stuff. And if you want to know where I am, you can see on the right down, I have the slide number. So you can watch where I am with the presentation. RWDI's key experiences, I'm showing like last time. We have been doing a number of long span bridges. A small list is attached here. And tall buildings, number of tall buildings. I think the one under construction is going to be the next tallest, Kingdom Tower, which is 1 kilometer tall tower. And many other towers, which I'm not quoting here. Not only just long span bridges and tall towers, we have been doing studies on many different types of structures. You can see diverse type of structures I'm showing here. just to give you an idea what kind of structures we are working with. Whatever is wind sensitive, it need not be like super tall building. It could be just look at the gate project in New York. I mean, the portal frames, which is not that tall. It's hardly, if I remember correctly, about 20 meters or so. There's a cloth hanging, and during wind, you know, it is oscillating. So we have done aeroelastic work on that particular project, and many other structures you can see, which is familiar. I think some of them could be familiar to you. So just want to let you know that, I mean, we have been doing diverse structures, not just bridges and tall buildings. Just to recap on the first part, this I gave a presentation. I think I gave a presentation about a couple of months back. I was talking about wind climate analysis, desktop stability assessment, section model test, 3D buffering analysis. We have discussed decks, pylons, and cables. Not too much on cables, but today I think maybe some more stuff on cables, but primarily on section model test and 3D buffering and wind climate analysis. So if some of you didn't have a chance to look at this, I mean, you can access this presentation, which is already in LinkedIn. So you can hear this video. Today, I'm going to cover aeroelastic internal study primarily. Then I'll be also touching upon vehicle pedestrian-induced vibrations, cable stability analysis, and if time permits, definitely into supplementary damping quickly with some conclusions. And then future webinar I'm planning basically on full-scale measurements and health monitoring and retrofitting. It's a very important topic because as you know that many bridges are very old in many parts of the world. They all wanted to know what is the health of the bridge, how we can improve the health of the bridge. So there is lots of monitoring going on and retrofitting. So this is a very important topic, which we won't be discussing it today. Like I told you, let us go through one by one. So aeroelastic is the primary topic that I'll be covering today. So aeroelastic model studies are undertaken basically to investigate the complex interactions between structural dynamics and the unsteady aerodynamic airflow over the bridge. So there are two things we are looking at, basically structural dynamics and the unsteady aerodynamic airflow over the bridge. So what is this structural dynamic forces? So we have to look at all three: inertia, damping, as well as elastic. As you know, simple dynamic equations where you have all three components. You have inertia, you have damping, as well as elastic forces. So it is a complex interaction of all the three. Has to be looked at it, and that's what you do with aeroelastic model studies. And aerodynamic forces, there are a variety of them. We have discussed some of these things in the last presentation: buffeting, vortex shedding, interference, galloping, flutter, all of those things. So we have to look at the structural part as well as the aerodynamic force part. So both of them together, you will get it in aeroelastic model studies. So when this is done, this is a very important part. After the section model test and the bridge stability is confirmed. So this is conceptually is very important because you don't want to do aeroelastic study right from the beginning, because before even confirming the stability of the bridge. So you can do the aeroelastic only after the stability is confirmed, because what if you don't go through that? That's a kind of a dangerous route, because if you straight away get into aeroelastic, what if the bridge stability is not good? It is failing in stability. Then you have to repeat the test, which is not good because that is very expensive type of testing. So you first have to make sure the bridge is stable, then you can do the elastic test. So it is more like a final study for fine-tuning the earlier results. That's what you are doing, but many things will be covered under aeroelastic study. For instance, 3D effects. That means the aeroelastic study is typically done for the whole bridge. So you have the deck, you have the pylons, you have the cables. So you'll get a overall 3D effects. And you'll get wind directionality effects because you can rotate the entire bridge. You can blow wind from various directions, various angles, and then you can get the wind directionality effects. And you can also get multimodal effects. So because, as you know, when you do section model tests, you're dealing with primarily vertical mode, torsional modes, probably first order, second order, things like that. But you can't simulate everything together. But in Aeroelastic, basically you'll get all kinds of modes happening. So you'll get a multimodal effect. So these are the fine tuning that you can do through Aeroelastic model stream. This modeling is very, very interesting. This is more like, I would say, kind of an artwork. You know, this modeling is very intense, in-depth modeling is required. This is not like a fun modeling of a rigid model of a tall building. It's not like that. It's very extensive. So we will see the kind of difficulties we are going to face while doing the elastic modeling. Shape is very important, of course, like in all studies, shape is very important. So that is more like an outer shell. You know, the outer shell can be printed, or you can also do either 3D printing or through handmade models, which can be done, outer shell. But it will be segmented. We need to underline that part. Segmented means the entire bridge, we cannot put one shape without any gaps. So that is what I call segmented, means more like 8-inch shells. After 8 inch, you'll have a small gap. And that gap is very important because if you put the shell all the way from one end of the bridge to the other end of the bridge, it will by itself will create a lot of damping as well as lots of stiffness out of the shell. And we don't want the stiffness coming out of the shell. So the stiffness have to be replicated using an inner spine system. There will be a spine which is going to replicate the stiffness, and that is separate. That will take care of only the stiffness. Then the shape is taken care of by the outer shell. The mass is by the shell as well as the stiffness together. And then the damping. Damping is supposed to be kept at very low, and you can adjust it. You can adjust that experimentally using artificial damping parameters. Because when you are building the bridge, you have to be extremely careful. Because if you are not careful with the joints and etc., automatically you will get a model which is highly damped. And that is not good. As you know, in long span bridges, your damping is very low. So you have to get a model which is as low damping as possible. And then you can add damping on and above whatever that is required. So typically done for slender structures such as bridges and towers. Floor number scaling is very important. I mentioned a little bit on scaling last time too. And in bridges, as you know, gravity is very important. So that's why floor number scaling is coming into picture. This is basic fluid dynamics. You can say floor number is V square by GD. So once you decide your length scale, your velocity scale is fixed. So it's kind of a very rigid kind of a criteria to take care in the internal testing. So there's lots of dancing around, I would say, is required in order to get everything at the right place. Elastic properties are concentrated in a spine, like I told you before, and that spine system is typically continuous, and that is typically being built using lathe. So you have to have a metal piece which is long enough, whatever the length of the model. But of course, you will have beams, you have deck sections, you have probably cables, etc., etc. All of those systems are separate. So, so those cables have to be connected with your spine system of the deck and etc. So you will have some joints. Definitely, you're going to have some joints. But when you are talking about deck alone, you don't want to have any joints on the deck alone. You will have one single piece likely going from one end to the other end. Otherwise, you may have to do some welding too, because I do have cases where we have done welding in spine systems. Length scale ratio and velocity scale ratio chosen to suit the size and the speed range of the wind tunnel. And I'm putting one table for how the scaling is done. For instance, you may be wondering what kind of material we are using. So whenever we are scaling, for instance, the flexural scaling of vertical bending stiffness and lateral bending stiffness, we are scaling basically EI. EI of the model, EI of the prototype divided by EI of the model scale should be length scale to the power of 5. There is a scaling which is already written there. So once you have the model scale EI, then you can pick a material, and that material, let us say aluminum or brass, then you know the E of the brass, and then you can divide, then you can get the I of the model scale, then you can decide what kind of section is required and things like that. So it's a very in-depth procedure. And since you have to satisfy a lot of things, I would say that's very, very challenging. Okay, especially vertical lateral is easy to satisfy, but torsion is not that easy to satisfy. So you have to be thinking what is important, what is not important, etc., etc. Look at the stay cable. Things are different. In stay cable, axial stiffness is modeled. So you have to consider not EI, so it is more of EA actually, elasticity in the area. Material used, plywood, balsa wood, pine wood. Basically in aeroelastic modeling, virtually you can do, you can pick any material you want, basically. Because I remember when we were doing the gate project, that is not a bridge project, but the cloth is hanging, so we have to virtually go to the clothes store to buy equivalent clothes and to have the same kind of, scale down density and things like that. So you can basically use whatever you want. Essentially, you have to get whatever properties that you're looking for in the model scale at the end. Carbon fiber, 3D printed plastic can be used. Aluminum brass is commonly used as a spine system. As a shell, mostly 3D printed or balsa wood. And the piano wire is being used for cables. For axial stiffness. I'm showing several bridges, just quickly going through. These are all aeroelastic models. This is US Olympic and Paralympic Museum, Colorado Springs. This is a pedestrian bridge. And as you can see, this bridge, the measurements, typically in bridge aeroelastic measurements, we do accelerometers. We use gauges as well as laces. Laces is primarily to measure the deflections. Once you know the deflections, you can convert it back to loading. So those cases kind of slightly discussed in the last presentation. This is Cooper River Bridge, Charleston, USA. This is at the construction stage. As you can see, the tower at the construction stage, it has shelves. You can't see the spine system in the middle. There is a spine in the middle going up. And then we are putting accelerometers to measure the tower leg, the accelerations. The moments are measured at the base of the legs. You can use gauges, which is being pasted on the spine system. So the spine system will have the gauges. At multiple locations, you can put the gauges and you can draw the wires down and you can measure wherever you want the moments. And the lasers measure the deflections, deck deflections, which is primarily we are using lasers. You can see the I-74 bridge under construction stage. Again, freestanding arch, which is getting vibrated during construction stage. So the construction stage is sometimes very, very tricky because once you connect those freestanding arch, the arch sections, then definitely this vibration is not going to be there. But during construction, it could vibrate. And you need to know in which months you are doing these constructions and what is the probability of wind happening at those wind velocities, causing such vortex shedding and oscillations. So this is a very tricky thing. And then you can also find out solutions in terms of what kind of solutions you can apply, like a temporary strut or a tie down cables or some sort of solutions can be derived. There is another vortex shedding induced vibration on the components of the fences, because these vibrations can come not only just on the main bridge, but also on the, even on the fence. So this is one of those examples. Finally, we solved this using hose dampers. We added some more weight on those pipes, and then these vibrations went away. So these kind of solutions can be derived right in the wind tunnel. And here itself, you can also do the scaling much higher, or even one-to-one. You can also see one-to-one testing done on cables, on fences, and things like that. One main bridge I'm showing is a Main Street Bridge in USA. So this is long back, this Aeroelastic model was done. This bridge is about 200 meters long. And this is a very complicated bridge with a vehicle deck and pedestrian deck, arch. There are struts and hangers and floor beams. And as you can imagine how complicated this Aeroelastic model could be, actually, you're going to see certain pictures of that. And the moment of inertia, I told you before, EI is being modeled, flexural stiffness in the x-axis, y-axis, and polar moment of inertia is being modeled as well. And you can see from scaling, like I told you, once you decide your length scale, your velocity scale is square root of your length scale. That's what float number, according to float number scaling. So then your frequency is also square root of square root of length scale. So in this particular case, the scale is 60. The model is built at 1 to 60. So my frequency, as you can see, the target frequency, sorry, the predicted frequency in the finite element model is 0.762, and the target is 5.9 according to the scale. And the actual model gives 6.43. But it is not exact. I mean, sometimes getting exact match is very difficult. So you may have to do some corrections once you get your results. So here there is 9% deviation and 14% deviation in the vertical direction. And damping was about 0.55% and 0.45%, which we are reasonably satisfied. In fact, this could be higher. So if at all vibrations are higher, then one may have to increase the damping as well at the model scale. So you can see some of the modeling technique. I mean, this is very, very complicated model. Because you have the spine system which is going through the vehicle deck. You have the spine system of the pedestrian deck, which is a kind of an inclined deck, as you can see on the right-hand side of the picture. Then you have struts, you have cables, you have floor beams. And if you look at the floor beam, you can see a brass piece. Basically, the floor beam was a brass piece. But then we added a balsa wood underneath the brass piece to mimic the actual shape of the beam. So the beam is very high depth according to the model scale, but we don't want the brass piece going all the way from the top of the flange to the bottom of the flange, because if you do that, then the stiffness is too much. So in order to reduce the stiffness, we built the flange very little, I mean the brass piece. Then we added balsa wood underneath just to mimic the shape. The balsa wood is not giving any stiffness, only the brass piece is giving stiffness. And there's lots of technique, and you can see the 8-inch shell. Here it is wooden pieces. So you can see there is a gap between the shells. There is a gap between the shell, even in the arch. Arch is also having a spine system. So it's one of the complicated model. So you can see in the construction stage, we took out the pedestrian deck. So these are the beams which is holding the pedestrian deck. You can see the nuts and screws and things like that. And you can also see the gap between the balsa wood and the deck. You can see that. As I told you, I mean, this, if you are connecting all the sections together, then the shell itself is going to give you some stiffness. And it is quite difficult to take care of that. That is why one need to be very innovative in building this model. You have to have spine system which is all attached together. Then the shell is just there to mimic the shape. So it will vibrate nicely, because if you are connecting it, it cannot vibrate. So the spine system will be vibrating. While vibrating the spine system, it will take the shells along with it. That's how this modeling is done. This is Takaman bridge, which is one of the long span bridges we have modeled in 1:211 scale, long back. And the model is about 7.5 meters long. And we tested in NRC's 9 meter by 9 meter cross section internal. So you can see the oscillations of the bridge, and with all of these modeling, you can imagine, I mean, how complicated they are. This model took about, I think, 4 or 5 experienced modelers. Took about 6 months to model this particular bridge, 2 bridges, because 2 bridges side by side. So we have to model both of them to study the interference effects, and that is very important. So one of the bridges existing already for many years, and the new bridge came after 50 years or so. So we built both of them aeroelastic and tested in the NRC town. This is another pedestrian bridge, Dubai Water Canal footbridge. You can see the vibrations of this bridge, and this is basically at this stage, you know, the stability has been already confirmed. So there is no question about stability at this stage. Okay, so this is more of I would say the 3-dimensionality effects and wind directionality effects and multimodal effects, and those kind of effects we are trying to find through this test. So here, I don't know whether you noticed or not how the cables have been modeled. Of course, it has the piano wire, but then it has some wooden pieces. So this is just to create the overall drag on this cable. So if you put the entire thing with that wooden piece, then the exposed area is too much. So you'll get more drag on the cable. So these kind of techniques, one has to be very careful, because at this scale, it's kind of difficult to model the cable. So you can model the stiffness of the cable. You can have the overall drag of the cable using these kind of techniques. So one has to be extremely careful in each and every piece that you put it in this bridge. You can also see the fencing, and that fencing will also be tricky at times, because you can't model exactly the way the fence are in the prototype. So one has to be very creative in building these models. Now the vehicle pedestrian-induced vibrations, and so Millevaert, France. So this is one of the famous bridges most of you might be knowing. And this bridge is about 2.5 kilometers long, and many suspension and many cable stayed sections. And the towers are some of the tallest towers, 330 meters or so. So in this bridge, one of the stuff that we were looking at is the traffic being affected by wind blowing against the bridge. So we want to reduce the gust speed affected on the traffic. So came up with some fencing system. So you can see the shape of the bridge is very fantastic shape with beautiful aerodynamic shape. And the shape is quite famous. As you can see, inverse airfoil shape and negative lift. And I'm not going through any of those details. As you know, the airfoil shape in aircraft wings, this is just a reverse of that. So you're trying to push down the wind. And as a result of that, you have a negative lift, which is nice. Then you have the fencing system, which is about 3 meters tall. And we are reducing with this fencing system 40% reduction of gust wind speed. It's about 3 meters height. And you can see the wind barriers, how the shape of these barriers and the testing in the tunnel. And 5 bar C cross section, 0.3 meter wide and 0.3 meter spacing. And no aerodynamic tone. Of course, you need to be very careful when you're putting up shapes like that. when you have gaps, you can create acoustical issues. So one has to be extremely careful. So we have to make sure those things are not there. And plus, it will reduce the gust speed which is occurring on the bridge. Such studies are quite common. Blowover study in the wind tunnel with traffic. And here, I think vehicle characteristics and aerodynamic effects of bridge superstructure should be simulated. And the vehicle can be wooden or plastic. And transducers are typically being used to measure forces and moments coming onto the traffic. And we can also find the critical rollover wind speed on a bridge, and we can come up with the traffic restriction guidelines. So these are some of the things that one can do. Of course, this is showing just one truck, but you can have multiple trucks. During a traffic jam, what happens to the bridge? Obviously, when there is a traffic jam, when all vehicles, all kinds of vehicles are getting clogged up, then you can have more drag happening onto the bridge. The question is, when these kind of jams are happening at very extreme high speeds or lower speeds, etc., and etc. So beyond a particular speed, you should not be allowing any traffic on the bridge. I think with this in connection, I was just looking at IRC 6 2017, and I saw that no live load allowed when deck wind speed exceeds 36 meters per second. And I don't know, I'm just calculated, this is 130 kilometers per hour mean hourly speed. It seems too high of a speed for allowing traffic to be on the bridge. And I found this is extremely high. So this is something that we should be thinking about it, because if you calculate the 3-second speed, then you'll realize that we are talking about 200 kilometers per hour gust on the bridge. I don't think we have to allow traffic up till 200 kilometers per hour. This is something I put for thought in the future. Recent trends, I think there are lots of pedestrian bridges at various types of sections are coming with single tower, with curved decks, etc., and etc. These are light structures. Like last time we discussed about pedestrian bridge a bit in terms of the mass, because typically bridges are lightweight and pedestrian bridges are very lightweight, and as a result of that, it can vibrate due to pedestrians and due to wind, etc., etc. So one has to be extremely careful while designing pedestrian bridges. And the comfort criteria that are out there, I think there are various codes discussing about that. I'm putting out certain codes here: ASC, Eurocode, Ontario Highway Bridge Design Code, ISO has some provisions, CETRA has some provisions, and etc. And unfortunately, the criteria are all over the place. Actually, it is no coherence between various criteria between codes. And the only thing I can tell you is that some of these criteria are relaxed in certain codes, and certain codes are very stringent. But just to give you some idea about the acceleration levels, in buildings, for instance, you are talking about 1.8% acceleration limit for residential buildings. You can imagine on this graph where 1.8 is. Very, very stringent criteria on buildings for obvious reason, because you are going to live in buildings. So you don't want the building to be vibrating on a daily basis and you feel the motions. But on bridges, of course, you can relax a bit because you get in and get out very quickly. So you're not going to be there for a long time, and etc. So we can relax it a little bit more. So, but this is something that I think I put for thought. I think in the future, a lot of research is required in terms of comfort because it's kind of very subjective at this point. Just want to show you Millennium Bridge oscillations. I think many people might have observed this in the past. The pedestrian vibration and the bridge is open. The bridge just started vibrating due to pedestrian walking, and some people are holding on to the rails, and some of them are in unison with the motion of the bridge, which means they are exciting the bridge even more, walking in rhythmic action with the motion of the bridge. But in an hour, this got closed and finally fixed through dampers. So the main issue was lateral vibrations due to people walking. Because as you know, when people walk, they walk at somewhere around 0.75 hertz to 1 hertz. They run between 1.5 hertz to 3 hertz, and they can jump between 3 to 5 hertz or something like that, you know. So there are, of course, you can also jump slowly or jump fast in a fast manner and things like that. But what I'm saying is that typical ranges of jump and running and walking, there are criteria out there. So one has to be very careful whether the bridge is going to get excited when there is a force coming from the pedestrian on those frequencies. So there are lots of studies happening nowadays on this. There's lots of research going on. And at RWDI, we are also doing a number of things, and mainly on time domain simulations. And we look at traffic conditions, like a weak traffic or dense traffic or very dense traffic. There are criteria again out there, what is meant by dense traffic, what is meant by exceptionally dense traffic. You can see from these descriptions. And then we build models, computer models, and we can have lumped system models with appropriately simulating the stiffness in the vertical, torsional, and lateral directions. And then we can force this, the placing of the legs and etc. as in time domain. And then you can get the response to the bridge directly. Like in a 3D buffeting case, like wind loading, we do exactly the same. Instead of pedestrian walking there, the wind simulation we do. We have stochastic models. We create wind in a pattern, which is coherent wind patterns, hitting the bridge and exciting the bridge. Similarly, you can create this very easily. Previously, we used to do this on a sheet. We know how fast a person can walk. You can have loading at different positions, different locations of the bridge, and you can excite the bridge. Now everything is fancy in a computer. You can get the response. You can get longitudinal, lateral, and vertical response. And then you can also even put a damper. You can see how the damper is effective or not, etc. Everything out of computer. And these kind of models are gauged against what happened in the full scale. So those projects which we have done, we have ample enough opportunity to measure it and recalibrate our own models to make sure the predictions are very good. And not only just pedestrian, equestrian scenario with horses walking on the bridge. And recently we are involved in a project in the Middle East where they were talking about carts carried by horses and people walking. There are multitudes of scenarios we have to look at it. In this particular bridge, we are looking at TMDs at various locations, how they are reacting to the motion of the horses. As you know, in horses, the motions are very peculiar in comparison to the pedestrians walking. And also the horse weight is much more than the human weight. So it's at least 10 times, approximately about 10 times more than the humans. So you have totally different types of forces happening on the bridges. So the main objective is to maximize the comfort of occupants. And you can model it, like I told you, like forcing functions. And you can have lock-in phenomena because depending on what kind of frequency you are walking, you can change the frequency of walking. You can have random walking. When a bunch of people walking on the bridge, all frequencies are not going to be the same. So it will be randomized fashions. So everything is possible to simulate in time domain. And the peak acceleration amplitudes can be obtained. And from this, we can say whether the motions or the response is acceptable or unacceptable, and come up with mitigation solutions in the form of supplementary damping systems. Now I move on to cable stability analysis. So cables are, again, important part of the cable state as well as the suspension bridges. And here, the power imported by the wind must be dissipated. And I'm bringing up an important parameter here, Scruton number. I think Scruton number is extremely important parameter in aeroelastic model studies. And this is a mass damping parameter because, as you know, whenever we discuss about vortex shedding, regardless of the shape of the structure, vortex shedding always happens. But at different frequencies, depending on whatever the wind is, depending on the wind speed blowing against that structure. So when the structure frequency is kind of near to the vortex shedding frequency, suddenly the motions are getting bumped up and very high motions can happen. And it can have lock-in scenario as well during vortex shedding. So that is one part of the equation. The other part of the equation, whether that amplitude is going to be higher or not, entirely depending on the Scruton number. Because the Scruton number is kind of a mass damping parameter. It depends on the mass of the bridge. It depends on the damping of the bridge. So in this case, cables, mass of the cables and damping of the cable. So here it is very, very unique. And you can see that as the Scruton number is getting increased, your response will decrease significantly. So you can have an equation, it is directly proportional to the inverse of the Scruton number with the power. So that is very important parameter. So whenever we do, before we do aeroelastic studies at the desktop assessment stage, the important parameter to be estimating is Scruton number. Then we see that where the Scruton number is sitting, whether this can cause enormous motions or not. So this is an important parameter. The excitation mechanism, there are diverse excitation mechanisms in cables. Vortex shedding is obviously one of the mechanisms. Rain, wind-induced vibrations, buffeting due to turbulence, which is quite common even in different types of structures. Dry inclined cable galloping is another type of excitation. Ice accretion galloping that happens typically in cold countries where snow is getting accumulated on the cables and getting ice formation. The shape of the cable itself is going to get changed to a different shape, and suddenly the galloping will come into picture. Because in circular shapes, typically you won't get galloping. Of course, in circular shapes, you can get galloping due to inclined cable galloping and wake galloping, because at certain angles of attack, one cable is behind another cable at slightly different offset positions, and then you can get wake galloping. Some of these parameters of excitation mechanism we have already discussed in my first part of my talk. You can see the vertical motion caused by resonance. I think the vortex shedding happening on circular cylinder, all the mechanisms which we were discussing in the earlier transparency has a very difficult to separate it out. I mean, vortex shedding all the time when wind is blowing against the cable, you can have wake galloping, you can have inclined cable galloping, and you can have vortex shedding, and the mix of everything together. You can have buffeting, because buffeting is always mixed with the vortex shedding. So depending on how intense the vortex shedding is, you can watch out for that from the spectra. The spectra is going to be very, very peaked when you have very narrow band vibrations happening, because all your energy is going to be at particular frequency in comparison to broadband spectra, where you have energy content in a lot of different frequencies. So like in every single case, the strategy for cable vibration is look at aerodynamically whether you can resolve this equation or not, this question or not. You can have helical rips. Nowadays, there are lots of techniques available. Longitudinal rips for taking care of rain-induced vibrations, which I haven't written here. Helical rips in the viaduct bridge they have used. So the first primary attention will be whether to change the shape of the cable, the external shape of the cable or not, to reduce the vortex shedding and other types of instabilities through helical rips or any type of other types of rips like longitudinal rips to take care of rain-induced vibrations. The other type of solution is cross ties. In Normandy Bridge, it is being used. In-plane stiffness can be increased using a tie which is connecting all the cables from the bottom to the top. So you can see those lines in Normandy Bridge where at multiple locations they are putting cross ties. And this will increase the stability of the cables. So this is another technique one can use. Sometimes multiple solutions have been used with the ribs as well as cross ties and etc. The last solution is damping. There are lots of different types of damping solutions being used in the cable vibrations. So the damping demands have to be found out. So again, we can estimate the cable natural frequencies and critical wind speed through an assessment. And then we can find out, what kind of damping demands is required based on the Scruton number calculations and etc. So one can do certain calculations upfront to find out what kind of strategy that we need to adopt, or a mix of strategies like crosswind and aerodynamic solutions as well as damping solutions. As far as damping is concerned, there are a number of different types of damping systems available. Some of the options are internal damping. There are lots of developments happen in internal damping. Inside the cable itself, there is a damper, or external damping systems are also available. I'm not going through any of those details, but you can easily find out from references. And you can see one of the cases where the cables are getting vibrated on a daily basis. These kind of vibrations are not found at the time of the design stage. The damping demands are not defined. And then later on, this issue came up, and finally the measurements have been taken and fixed through damping solutions. So one has to be extremely careful, about these things. But I think primarily many of these things can be found out through an assessment at the beginning. Then later on, if it is required, you can go through detailed studies. And as you know, that these vibrations, even if it is not huge over the period of time, it will accumulate. A lot of fatigue failure can happen. And some of these fatigue failures you can see in certain other bridges, plate fracture and some other types of failures. So like I said, how do we take care of this? Cable vibration study, we can start with the desktop assessment. This is very important. And like I told you, with the properties of the cables, with the frequencies, with the mode shapes, with the wind speed at that location, with the wind climate study, for instance, and you can find out at what frequencies you are expecting VIO, and what would be the amplitude, approximate amplitude which is going to happen, and how many cycles it is going to accumulate, etc., etc. So from that, you will have an idea, like what to do, how to resolve that particular issue. And if you want, you can go through elaborate wind study. In terms of galloping vibrations, as well as static force coefficients can be found out through wind study. 1:1 scale prototype, 3-meter long cable with the ribs or LED lighting. In certain cases with ribs, you can do the testing. And also LED lighting, because I know a few cases where the cables have been planned, everything done, and then finally, suddenly they want to put lights on the cables to lighten up the bridge. But this wasn't planned earlier. So that is not very good, because when you put LED lighting on the cables, it's going to change the shape of the cable, and you can get galloping vibrations, you can have problems. And that needs to be tested. So that is the use of such test. 3D section model rig can be utilized. You can have lateral, vertical, torsional motions for these cables. And you can attach strain gauges and accelerometers and laser transducers like a typical section model test. Similar situations, you can use it. Here, you have to rotate the cable at multiple angles of attack because these LED lighting would be at one location. So you have to see the effect of wind coming and hitting the cable from various different angles. So that is very important during this test. And another elaborate test is rain wind induced vibrations. And this is also an interesting test. 1:1 scale prototype, 5-meter long cable can be utilized. This can be tested in 3-meter by 6-meter NRC tunnel. This is a dynamic rain wind test rig. You can produce the rain at a particular intensity. The rain rivulets will fall through the cable, and then you can assess the vibrations of the cable. And here too, strain gauges and accelerometers and laser transducers can be utilized. Cable inclination, rotation of the cable, like I told you before about longitudinal axis will also be simulated depending on the ribs and depending on what kind of architectural features are there on the cables itself. You can see a mock-up full-scale test, model test in the NRC tunnel. This is a huge testing facility, and these models are quite, these are actual models, 1:1. Now, the last portion of my presentation is supplementary damping. And here, this is, as you know, that one of the options for reducing the oscillations or restricting the oscillations. Initially, you always started thinking about architectural fix, aerodynamic shaping first, before even you think about the supplementary damping. The structural fix is not quite common in bridges, but a lot common in buildings. You play a lot with mass and stiffness, but I'm not seeing too much of that thing in bridges. But mostly we start with aerodynamic shaping, which is very common on deck sections and things like that. Then ultimately, if that is not, I mean, that is not enough, then whatever is remaining is solid through damping systems. So basically, these are passive damping systems. So a large body of mass oscillating out of phase with the primary structure, dissipating precisely the right amount of energy per cycle. These are passive systems, no powered drive mechanisms. You can also use active systems. I think certain other vendors are doing that. So from where you are getting the structural damping? I mean, inherent damping is internally, it is being created, or externally. I mean, in bridges with materials, contact areas, and soil is also giving some kind of damping. So those are the inherent damping, which is on any structure that you take. In addition to that, you can add supplemental damping. So inherent damping sometimes is kind of uncertain and very low. And it's kind of a debate in some cases, what would be the proper damping for a bridge is concerned. But based on experience, it is varying from a certain range to a certain range. Based on experience, one would pick a number in terms of inherent damping when you do bridge studies. Then later on, you can confirm that through testing. Once the bridge is constructed, you can excite the bridge and find out what exactly is the damping of the bridge. Then if it is required, you can add damper as well. And even though I said earlier, large body of mass, which is not quite true as far as bridge is concerned, because a large body of mass is typically true for buildings. Because in buildings, the damper could be very extremely large weight. We have installed the biggest so far is 1,300 ton on a building. But in bridges, typically 2 ton, 3 ton, 5 ton. I think maximum we have done so far is probably around 5 tons or so. So the trick is just to reduce the response. So without TMD, you will have a peak response, and with the TMD, it will come down. So you can find out the adequate damping which is required to reduce the response, which is simple to find out from internal test or through analytically. So in this particular bridge in Wichita, we have used a damping system. So you can see 2 different types of vibrations. One is vertical and another one is lateral. So you can simulate these kind of dampers underneath the bridge very easily, and it can be hidden underneath. So you won't even see certain bridges are having dampers. Of course, with the cables, you may see some of those dampers outside, unless otherwise cables are having dampers in certain cases inside the cable itself. And all of these designs are typically done using computer simulations. You can do time domain simulations of these dampers. You can design everything using computer simulations, and finally you can do some mock-up test inside the lab, and eventually you can do commissioning. You can construct and commission it. So while commissioning, you need to do some certain full-scale tests to find out what exactly the damping of the bridge as well as the frequency of the bridge. Another tune mass damper that is being installed in this particular bridge. You can see vertical vibrations without a TMD and with the TMD is being shown there. And you can easily see the influence of tuning, because if it is out of tune with the frequency of the bridge, then the damper is not very useful. So it has to be tuned according to the frequency of the bridge. So because of that, you need to find out the actual frequency of the bridge after the bridge is getting constructed. You can drop down weights from the side using cranes or something, and you can excite the bridge and you can get the vibration frequency of the bridge as well as the damping of the bridge. And then you can tune the dampers. This is also showing with and without the influence of the damper. Obviously, there's no surprise. I mean, with the damper, it is supposed to decrease the response. That is why we are putting the damper. So if you are not tuned appropriately, obviously the response is going to be very high. Like I told you, bridges are getting dampers not to the level that building is getting. I mean, building dampers are quite heavy in comparison to the bridge dampers. So here, Madison Square damper on the pedestrian bridge above the stadium, you can see 5 TMD weigh 5 tons each installed on this pedestrian bridge. So this is one of the largest damper. I've heard that another probably up to 6 tons installed on another bridge in China. That's the end of my talk, and with some conclusions. Aeroelastic test accounts for 3D effects, wind directionality effects, and multimodal effects. I want to stress the fact that these effects likely you won't get from any other type of bridge test. For instance, if you are doing section model test, you're not going to find 3D effects and wind directionality effects and multimodal effects. But by saying that, I'm not in no way pushing for aeroelastic test. Don't take me on the wrong side. Or I just want to say that some of these effects are important in certain cases. In such cases, aeroelastic effects have to be, tests should be done. And that will fine tune the results, and likely your loading will come down too, because you'll have all of these various effects which was not there in section model test. Maybe your amplitudes are amplified in the section model test or something which you can fine tune through Aeroelastic test. Aeroelastic model test could fine tune the results and from section model test and 3D buffering analysis. And in fact, the 3D buffering will take care of a lot of multimodal effects and things like that, including 3D effects in 3D buffering analysis. And then you can, when you do the Aeroelastic test, you will get the deflections, you'll get accelerations, and you can reconfirm your 3D buffering loads, what is coming out of the elastic deflections and accelerations. So that is another advantage. You can reconfirm the loads coming out of the 3D buffering analysis. Vehicle pedestrian induced vibrations require adequate attention at the design stage before it is too late. All I would say is that start with an assessment. I think in pedestrian wind-induced vibrations, we are doing assessments, including time domain assessments can be done. I mean, because you don't need any wind tunnel test for that. You can do everything in time domain, including vehicle-induced vibration. In vehicle-induced vibrations, you can also do the effect of road roughness and things like that. Because I remember a case where we were doing a pothole effect on the roads and stuff like that, because you can have a pothole on the road surface, then the wheels are getting into the pothole, it is going to give you impact loading. Now, how much impact loading it is going to create to the bridge, what kind of vibrations are coming, whether it is acceptable or unacceptable, etc., etc. So which will define very quickly how quickly you have to do the maintenance work and etc. So that's also very important. Cable stability issues shall be investigated at the design stage. And here too, you can do a desktop assessment at the beginning. And very seldom it will get into a number of different types of testing. Typically, desktop assessment is sufficient in this case. Supplementary damping is probably the last option in controlling response in the absence of aerodynamic and structural tuning, because I remember cases where aerodynamic solutions are suggested, but the client is not doesn't want to change the shape of the bridge. Eventually went with the supplementary damping. So they have dampers underneath the bridge, and nobody is going to see, and the shape of the bridge is exactly what they have envisioned and things like that. So you can go either way. I mean, whether you want to add this shape to the side and solve the problem that way, or don't bother doing that and put the damper underneath and solve that problem. But I have to warn you that typically the way the bridges are going is the aerodynamic shaping is very, very important. So you don't rely too much on the damping. You solve it on the shape itself. In many cases, that's what is happening. Supplementary damping comes in later stages. That's about it. And with that, I conclude my presentation. I hope I gave you a rough idea about all of these various topics in bridges. And depending on the case, we may have to do certain studies, or we may not have to do certain studies, which I think an expert can advise. And we can advise which studies to be done and studies it's not required. With that, I conclude. Thank you. Thanks for the opportunity, and thanks. Hello.
Hello. Can you hear me?
Yeah, again, just go ahead.
Yeah, I lost the net.
Oh, you lost the net.
Yeah.
Okay, no problem.
Just restored.
Right.
Okay.
I believe in the meantime you completed your concluded your talk. Yeah. But first of all, of course, thank you so much. It has been a very, very clear presentation of your thoughts and issues that you covered. but that is usual with you, so I don't have too much on this. You have very nicely touched upon the issues about aeroelastic modeling, and I am happy that you clarified that we should first ensure that it's a stable design, then go for fine-tuning with aeroelastic modeling if it becomes necessary. Which, you know, the aeroelastic model can cover other aspects which the sectional model cannot cover.
Yeah.
But very rightly you pointed out that we first must ensure that you have a stable design.
Yes.
So that's one thing. And then you mentioned very rightly about this, talking of loading on the bridge. And you mentioned about the IRC specification of 36 meters per second. Very interestingly, I was talking to Dr. Lakshmi yesterday evening, and saying the same thing as you did, that it seems very unreasonable. This is too high wind speed, above which we say vehicular traffic is not there. I'm sure a much lower speed can be thought about. It should be reviewed.
Yeah.
In fact, there are, I'm sure you all know about bridges. Kakashi Kakyo Bridge does not permit vehicles above 25 meters per second.
Okay.
And similar limits may be there elsewhere.
Yeah.
So 36 is way above this kind of threshold value that is being used.
Yes.
In fact, I also think that if you have a pedestrian bridge,
yes.
What kind of wind speed are you going to say is the limiting speed above which we don't expect full pedestrian traffic on the bridge?
Yes.
And even it may be less than 25 meters per second.
Correct.
I can't imagine 500 kilogram per meter squared pedestrian traffic along with even 25 meters per second.
Yes.
That's too high.
Yes.
They'll all disperse, you know, if you have a storm like that.
Yeah.
So I think that's something which needs to be reviewed, and Dr. Lakshmi did say that you know, it's being reviewed.
Yes.
The whole thing is being looked at.
Correct.
Yeah. Then the comfort criteria, you very rightly pointed out, and again, my own thinking in this has been that we need not be too stiff on comfort criteria in bridges. Pedestrian bridges, of course, we are talking about pedestrian bridges. We shouldn't be too stiff on this. I think some of the specifications abroad are probably too stringent in as far as comfort criteria is concerned.
Yes, I have a comment on that particular aspect, because I remember one case where the bridge is about 1 kilometer span and it never got constructed. Then when we did the studies, we found the deflections were at, it is passing based on the AC criteria of 5% G, but the deflection is 0.7 meter on that bridge. 0.7 meter is acceptable based on the criteria. So it is very deceiving sometimes, because one has to be very careful. The criteria is saying it is acceptable, but the deflection on the bridge is 0.7 meter. And as you know, 0.7 meter water shedding on the bridge is not acceptable. So we ask them to change the shape of the bridge. So either way it can happen. Sometimes it is too stringent, sometimes it is too relaxed. So I think a judgment is always required in terms of...
we need to look at this very carefully, I suppose, all these issues. Then about the cable stability issues, I think you are very right that very careful desktop study should be done.
Yes.
I think more or less one should ensure, even if one has to be conservative a little bit, to ensure that things don't start to play up, you know, in the prototype. Because it is two things. One, to do retrofitting is not simple. It's a complex affair. Secondly, it gives a loss of confidence amongst the using public. If you see a cable vibrating like anything,
Yes.
large amplitudes,
Yes.
then lots of confidence that you will get. So I think desktop analysis, and perhaps, as I am saying, maybe even a little conservative
Correct. Correct.
in that sense.
Yes.
And also you touched upon damping, always a tricky issue. Well,
Yeah.
thanks for touching upon damping as well.
Yeah.
So thank you, Dr. Suresh, for this very fine lecture. May I, in fact, now go to our panelists? Can I ask Professor Tandon if he's there? Professor Tandon, Mahesh Tandon? Oh, he's there. Yeah.
Yeah, is that? Yes.
Yes.
Muted, sir. Muted.
Okay. You unmute, please. Yeah.
Yes.
Yeah, go ahead.
As usual, fantastic presentation by Mr. Suresh Kumar and Dr. Suresh Kumar, and it is really wind engineering made easy. I think that should be the title of the book, or the lecture. No, that is very nice. I only wanted to mention one thing, that this terrain, the ground terrain, has a tremendous effect on the wind effects.
Yes.
And I think they can be modeled only in the, if you have a full aeroelastic model and you model the terrain, only then you will get the the required effects. That's the only comment I have, actually.
That is true. That is true, because typically your elastic models are done at 1:200, 1:100 scale. In comparison to section model tests, you typically do at 1:40, 1:50 scale, where you have partial turbulence simulation. You don't simulate the full turbulence. The reason is that you can't simulate the full spectra. You'll simulate only high frequency part of the spectra.
That's right.
So your turbulence levels are slightly lower in section models in comparison to the full scale aeroelastic model. And plus you will get 3D effects and the wind directionality effects. You can rotate the model. So you can have different wind directions and multi-modal effect. There are a number of things one can get.
Yeah.
Elastic, yes. Go ahead.
Hello. Any other points, Mahesh?
Not yet.
Not yet. Okay. Okay. Can I then request Dr. Lakshmi if she has any comments?
Excellent presentation by Dr. Suresh, and he has, I think, touched upon the various aspects of cable vibration, and also he talked about the tests which can be conducted on cable with respect to rain wind induced vibration, where the rain can also be simulated inside the wind tunnel along with the wind. But I want to ask you, like the rain, the wind speed at which you will be doing the tests are quite small, and also whether the enhanced damping of the cable, they are also simulated when you are doing the test. That is, you do it without enhancing the damping and with damping. Both the things are done.
Yes, both the things are done. In fact, the damping can be controlled very easily in the tunnel, because you have nowadays magnetic dampers available. So you can, whatever the anticipated damping in the full scale can be simulated in the you can't say that the cable testing is at model scale. It is at full scale, because the actual piece of the cable is getting tested at 5-meter cable, the actual cable. Then the end conditions will be simulating your frequencies and your damping.
Yeah.
The actual cable is being used. So that means you can have the rivulets, you can have the ribs, you can have LED lighting, whatever you want to code it, and the damping you can simulate, and the velocity, because this test is done at a much higher velocity. You can simulate a very high velocity, up to 50, 60 meter per second wind in the tunnel. So that tunnel can create such high wind speeds. So you don't have, you can do more like one-to-one simulation. One-to-one simulation, not the entire cable, of course, a piece of the cable, but the properties have been simulated in the time.
Yeah, the one which you showed, the cable
Yeah.
was vertical,
Yes.
but I have read that some of them, they do it with inclined cable.
Inclined, yeah, we can do inclined cable. Yeah,
Okay.
inclined cable we can do.
Okay.
I've seen it. I've seen it done in a lab in Japan.
Yes, yes.
They were using the inclined cable. Actually.
Yeah, inclined cable. Actually, the photo that I showed, I believe that it is inclined cable. Just a minute. Yeah, this is inclined, actually, inclined cable.
Oh, it
That's
is
an
inclined.
incline. What you
Yeah,
showed
it
was
is
an
inclined.
inclined cable.
I see. I see. Okay, Dr. Harsh, please.
Suresh, thanks so much. I mean, it's been a wonderful series of lectures, starting with Dr. Lakshmi's to yours. I thank you for increasing our sum total of knowledge on this often difficult to grapple with subject of wind engineering for a bridge. Of course, the susceptibility of a suspension bridge would be far more, the critical wind speed effect for a suspension bridge would be far, far more an issue than for a cable stayed bridge. In India, we don't have pure suspension cable bridges yet for very long spans, maybe moderate span suspension bridges, which are not so drastically affected by the critical wind speed, first of all. The other is the importance, I think, which you gave to us. Thanks again for that. All these tips that you give us are all finding their way into our guideline. You'll be rest assured. And you will be asked to proofread the same. It is important as we go about building so many more such bridges, longer span bridges. It is important to have the wind loading on and the wind effects on our cable bridges and our suspension bridges. Coming to the point that you made, very important to alert the audience that you must first do a cross-section model, get the lift, drag, and torsional moment caused characteristics, the 3D effect characteristics for the coefficients, what we call coefficients, out, and understand first that part of stability under some moderate turbulence, and the higher frequency, of course, not being considered. Rather being considered. Now, coming to the issue of then taking this understanding and then going for a full aeroelastic model, you explained to us very clearly the complexities of the model itself. First of all, the vertical scale, I mean, the scales that you have to consider, the velocity, the length scale and the velocity scale, and the difficulty in coming to that actual basis, first of all, and the parameters of the structure that you would consider to bring in the prototype, as you called it, to the model equivalence that you need to get to derive first the length and then the velocity scaling coming almost directly from that. And that, of course, you explained extremely well to us based on Freud's number. That is a very important thing. And then the way in which the wind tunnel actually works, many of us may not have seen a wind tunnel in action or working, and how measurements are taken in a wind tunnel and what you actually measure in a wind tunnel and how it comes back to coherence in our work as a bridge engineer. So no doubt it's a complex kind of process, but what we are trying to understand here is what we need to come to a specialist like you with. What are our requirements as a bridge engineer, and when do we, having given us results, how do we interpret them? So I think that's what you've demonstrated to us. And the next few series of lectures will further probably show that if these are the outcomes, what are the issues to deal with, like we've had in our previous lectures from Professor Svensson on the examples of the Helgoland Bridge and a couple of other bridges which he spoke about, and how the actual values from the aerodynamic study are incorporated into characteristics or mitigation measures in live bridges, as you also showed us here. So that's a very important point, alerting us on the 130 kilometers per hour, which translates into a roughly about 200 kilometers per hour, three minute gust kind of consideration. So that is way too high. And I hope you never build cable stayed bridges with that allowance in the future. If we've made that mistake, we may have to do retrofitting and correction measures for the existing bridges if it is so. The comfort criteria you spoke about is, of course, to do with many things like footfall vibration. But the point really is that the intermodal effect is often combined with wind. Wind will be there along with footfall vibration, along with these two combining together is another dimension which we need to address. So the wind tunnel study for the wind part, and then the footfall vibration comfort study, which you showed to us, have to be in some way coupled, and it may not be by linear superposition because the effects may be non-linear. So these are issues that we'll have to grapple with, okay? But coming to the issue of the cable stability, which you again brought about, the most important point is earlier, even suspension cable, points that I'm adding, as it were. The suspension bridges, the cables would be, up to about 300 mm, 400 mm, the old style suspension bridge cables. But today, rarely we're going to cables which are more than 200 mm. That's simply because D is so critical in your screw-turn number. And the cable itself is so much affected by the D, the diameter of the cable. So bringing down the diameter has been a very, very important development in ensuring stability for cable stabilities over time. Then you also brought about the various mitigation measures that, what if you have a problem, how do you fix it? That was very well demonstrated by what you call the architectural fix, which is the aerofoil type shaping, and so then the structural fix, which you called as, the structure has mass and stiffness, which you can play around with to bring your structure within limits. Then the supplemental damping, which those 3 or 4 measures which you showed us about tying down the cables in the vertical plane or introducing dampers within the cable or external to the cable, and various patented mechanical and hydraulic and viscous type damping devices that are available and patented worldwide. These also we had covered in our cable stay course. So they are very welcome, those additional information you gave us. And I fully agree with what Professor Prem Krishna said, that an afterthought is an afterthought, retrofitting, get it right the first time, do it right before you build it, rather than build it and have a problem on your hands like the Millennium Bridge and try to solve it. That is, I would say, in a sense, bad engineering and bad conceptualization. So the conceptual studies, case studies that you would have looked at to arrive at your form and the wind climate that you have, and then your quick off-the-desk type calculations and approach which you have should home in on a reasonably good conceptual study preliminary design, including wind. So the importance of wind in the preliminary studies is clearly spelled out for increasing spans and even for short spans when you have lighter structures for pedestrian bridges. It's not only the span. So these are sort of comments that I want to add to your wonderful lecture. So let's have it the next time when we go for our retrofitting measures and other things that we missed out, announcing lecture 3. Participants have been praising you for that and have been asking when the next one will be. So I'm preempting our moderator by requesting on behalf of ISTRUCT to consider the 3rd lecture, and we would look forward to announcing it shortly. Right. So that's all I have at the moment. We should.
Okay. Well, thanks a lot for very, very valuable comments, Dr. Harshvardhan. I think together we've had a very rich outcome today from today's lecture. There are some questions, and let me just go to these questions. During the wind test, there is considering any temperature variation during the wind test?
Not in our tunnel. For instance, if you're doing wind tunnel test for bridges in cold countries, and you have ice accretion on the cables and etc., those type of tests cannot be done in the tunnel that we have. So those tunnels, such type of tunnels are available. So very seldom we do such tests.
Then we have a question here. We bridge engineers now know some details about the model study and how much detailed working is required to prepare the model, and how meticulously even the materials for the model needs to be selected Very, very true. Absolutely so.
Yeah.
Yeah. Very true.
Very true, sir.
It's
The
a,
complexity.
yeah, I think it's a different ball game.
It
The
is different.
aeroelastic test and the section model test.
It is totally different. The modeling is a piece of artwork, I would say.
Yes, yes.
And I have to say that I give due recognition to these kind of models to the modelers. We engineers are nothing in comparison to modelers who does the modeling. Because sometimes we design things on a computer and say, okay, this is the section, that's the section, go back to the model shop. The modelers will say, this is not going to work, Suresh. You don't know how to do it. We'll do it for you. You know, they are such experts, you know, they know, because they play with the materials. They play with the screws and nuts and everything. They know exactly how to do the modeling. So you just have to give some numbers. Of course, it is all based on scaling and numbers. And then they will give you some suggestions in terms of, okay, we do this way or that way. And so it is a totally an interactive game between an engineer and a modeler, and finally come up with a successful, model.
Yeah.
Very true.
You know, considering this, considering the amount of effort, the skill, effort, time, cost that is involved in a full model.
Right.
On the basis of the sectional model studies, is it possible to venture whether you require a full
we can
test
actually.
or not?
We can, because in many cases, we also suggest that probably an aeroelastic study is not required in certain cases. For instance, I remember one case, that the bridge which I showed today, the detailed model with the vehicle deck, with the pedestrian deck and etc. In that particular case, actually, the aeroelastic test was not really required. Even though the client decided to do that, they did the aeroelastic testing. You know why it was not required? That is the interesting part. Why it was not required is because once the stability has been checked, it is stable, then we came to know that the wind load is nothing in comparison to earthquake load. So the earthquake load is already overtaking the wind load. There is no stability issue already. Then why are we doing aeroelastic model test? Right? So we can decide, we can make such decisions based on the scenario. We can say that, okay, this bridge is already stable. We don't have any concern about stability because that has been confirmed either through desktop or through section model test. Then the design is taken over by earthquake. Then our business is over in wind actually. We don't have to do any more internal tests on it. So it all depends on the case by case basis. We have
case by case.
Yeah,
on the other hand, if you have a topography around you, the terrain, which is complex, then there's a case for perhaps.
That is true. That is true. That is true. But mind you that topography is been already tested. The topographic model has been already tested for several kilometers of topography. And then you already know the turbulence which is acting at the bridge deck level and the tower level, etc., etc. Then when you go and do your aeroelastic, you are just modeling only a piece of the block at the edge of the bridge with the mountain sitting at the edge of the bridge. The bridge is just crossing the mountains or something like that. You don't get any other piece of the mountain because you are modeling at much higher scale at 1:200 or 1:300, where you won't see all the topography. You will see only the mountains on the side only. So again, this is a kind of I would say one has to think about all of these things before we get into.
Okay, great. Yeah, thanks.
Can I say something?
Yeah.
Oh, sure.
You see, our the clients or the owners, they also need a lot of education.
Yes.
For example, the number of times that they make you do a wind tunnel study for an extra dose bridge doesn't make sense. I mean, extra dose bridges are like other cantilever bridges, maybe a little short in height, that's all. The area which is exposed to wind may be slightly smaller, because it has got lesser thickness. But other than that, the cables are so short and they are so with such a low angle that even that is not a problem in extra dose bridges. But we still, uh, we have a hard time to convince our client that it is not required, but they say it is in the tender kind of thing. So you have to do it. So I don't know what your views on the subject are, Mr. Suresh Kumar.
My views on the subject is that it should be left to the experts to decide what type of studies are really required for that bridge. The experts have to decide, because the thing is, for instance, when we see the bridge, we say that, okay, an assessment, a computer model, sufficient for this bridge, done, no testing. There are a number of cases we suggested that way. But they come back and say, okay, this is already in the tender. So then the next question is, okay, who wrote the tender and why the tender is saying that, and etc. Okay, sometimes it is not required, but who is supposed to be dealing with that? I'm just openly asking to all the panelists here. I mean, those who are doing studies on those type of problems should be deciding, rather than somebody who is not doing any studies on
absolutely, Suresh. Absolutely. I mean, wrongly writing a tender document is to do it wrong at start.
Yes.
There is idiocy, what I would call idiocy. Sorry, but I must use that word. Yeah. In an extra dose bridge, there is absolutely no necessity to do a wind tunnel test. Even a cross-section model is defeating the purpose, because the torsional stability is assured by the box. You've got full torsional stability. The question of flutter ever arising due to slenderness will never happen. The cable is never going to gallop, and there's no question of any wake, because two cables are never close to each other. So actually the phenomena are ruled out. Then when the phenomena that could happen are ruled out, why specify some testing which is absolutely not required?
You're absolutely right. See, the problem, what I am seeing in India, not only just in bridges, but also in buildings and other types of structures, is something is written somewhere which has been written for the last 50 years by somebody. And we want to exactly follow the same. Unfortunately, see, the time has changed, the knowledge has increased. We know a lot of things after 50 years now, with all these studies done and etc. Why can't we change those documents and change it? But we have reluctance in changing that, and we need to, as a group, as panelists, I would say we have to change that. Unless you change that, this is what is going to happen. Because in another bridge, I remember, we said no tests required and etc. And then the client said, no, we want to do the test. So they were insisting for the test. And finally, what happened? Everybody wanted to visit Canada. And eventually it is all boiling down to a visit rather than the test, actually. So what I wanted to say is that let us be truthful to the science, and what is required is what is required, and that is exactly what we are supposed to be doing, instead of wasting our own money, right? The money is also getting wasted, by the way. It is not just about this, because I know a few other cases where they wanted to use a different velocity, a different wind speed, which is not even in the code, actually. Because we ourselves are trying to find out a problem, what is in the code, and they wanted to just increase the speed. So we asked the question, okay, from where did you get the speed? They said somebody measured somewhere and etc. There is no clear indication where it is being measured, but we are supposed to be using that speed. Whose money is getting wasted? That speed is not going to happen. This is just a waste of our resources.
So at least in the tender document, the statement of the critical wind speed should be one fundamental parameter must be stated, and verification of that should be assured first. I mean, maybe by model studies at site, by looking at the wind rosette, by developing the wind climate. The wind climate declaration should be part of the tender document.
That is a very, very important point, because with the wind speed, I'm not getting into the whole stuff about wind speed, but I just want to know, when you deal with bridges, you are supposed to be doing not just 100-year speed, you are also looking at 1,000-year speed and 10,000-year speed. How do you get those? You just go to table 1 and use that, right? Your speed is going to be extremely high. if you use that. So I have a totally different opinion in all of those things. Probably we don't want, this is another topic which I don't want to get in. But I would like to say that wind speed is very, very crucial. That is one of the places we keep making mistakes.
Correct.
And that speed is, we have a notion that when you use a higher speed, you're safe. But that notion is not correct, because things can fall at lower speed, and we have been taught by Takuman arrows on that, because the bridge is designed for very high speed and finally it collapsed for low speed. So we already have an example in front of us. So things won't stay until for the bigger speed, it will come down even before that. So I think we have to spend some time on wind speed for sure, yes.
I think very, very crucial, because for one thing, you do something wrong with the wind speed and you square the problem.
Right.
You make a mistake of 10% in the wind speed and the forces are 20%.
20%. Yes.
You know,
Yes.
so it is very crucial issue.
Very, very crucial, yes.
Some questions.
And another point I think I wanted to raise, because on the scaling, because I think Dr. Harshvardhan mentioned sometime before, typically the scaling is designed, scaling of the model is decided based on which wind tunnel you are using. Okay, because the wind tunnel has its own limitations in terms of the size and in terms of the velocity, because the velocity is very crucial. So let us say I have a tunnel where I can go only up to 15 or 20 meters per second. So I work backwards. I take that 20 meters per second, I square it, I'll get my length scale, and then I do all the rest of the logistics. And plus I have to also make sure that my VIO is happening at a low speed. Maybe some tunnels are not very stable at low speed. The fan is not very stable. You won't get a stable flow. So you have to decide where your vortex shedding is happening, where your strength design is happening, how my wind speed range is going to be fitting in my tunnel, whether it's everything is going to be okay within that range or not. So that is what is being the decision maker as far as the model scale is concerned. So your model scale will come out of that.
So the wind tunnel is the critical thing, yeah? The wind tunnel is, you work backwards from that. Thanks.
Yes, work backwards from that. Especially in bridges with float number scaling, you're kind of stuck. You're really stuck with float scaling, because in float scaling, the very important thing, because when you deal with typical Reynolds number scaling, you fix your length scale, your velocity scale could be anything. Then based on that, you can pick your time scale and frequency scale. It is very easy. Three things can be decided separately. But with float number scaling, you fix your length scale, you're done. Your velocity scale is fixed, your time scale is fixed, your frequency scale is fixed. You can't change anything. So it's very, very crucial type of modeling.
I think Professor Prem Krishna lost his connection.
Oh, he lost his connection.
So we can take some of these questions. Can you read them?
Dr. Harshvardhan?
So let's take a few random questions, because what questions are, Professor Krishna may be back.
Yes,
sir. Go ahead, sir.
Sorry, I got disconnected again.
Go ahead, sir.
Yeah, what I was saying about the codes of practice having such a long interval between which they get revised. The wind code, 87, 2015. And I was asked to write a draft code in 2002. So I wrote one in 2003. And so now what I'm saying seriously, these affect so much. What we do in practice, that we have to take it more seriously, these things.
Exactly. See, where the bureaucratic thing is coming into picture, for instance, the wind code itself, IS 875. I was recently looking at the IS 875, and I have written a paper, which is part 1, which I am trying to think where I should be publishing, with all the kinds of errors in that, and how to change things and where to implement things and things like that. This is something, and I have to write a part 2, which is more elaborate and things like that. But what I wanted to tell you is that if I put my mind into it, I can do everything in 3 months. And some other experts can review it, and we can publish it within another 8 months.
Yes.
It is only that, it is not that difficult actually. But who is pulling us down? What is pulling us back? And we need to be telling something today, what is required today in the industry, because the industry people are just using this as a Bible, and they are utilizing IS 875. And if there is something there which has to be cleared, it has to be cleared now. It should not be cleared after a while, and they might have already used this for a number of structures, you know. So I'm very much towards this, and but the system, you know, has to give adequate, you know, they should take it up actually, especially on BIS.
Yeah.
You see, this has to be taken up by some association or something like that, because, for example, IRC6, which is the loading code of you know, for roads and bridges, we have made 3 documents. One document is an explanatory handbook. That means that it tells you what is the clause and what it means. That's it, without putting any subjective information in it. The second one is to make a few solved examples. That means that if you are going to use this code, how do you go about it? That should be there. The third document is that how it should be corrected. There are 3 separate documents, and that is how we are handling it in IES Shakti's you know, sort of a guideline or whatever you want to call it for IRC6. I don't know whether Alok is around. He's the person who took the initiative, and we have done it. But of course, we have run into problems. Run into the problems means that you cannot have. They say that if you put the text on one side and the explanation on the other side, who will buy the original code? So there is a loss of you know,
Lots of revenue.
So you never know what kind of hurdles you are going to come to. But I think that there is nothing wrong. Anybody can write a book on wind engineering and take the clauses there and give the you know, the opinion. The third type of thing that I think can certainly be done. Nobody
Yes.
can have any objection to that.
Yes, yes. That's the direction I'm going. Sir.
Okay. I think there are questions, but I don't see them on my screen. Dr. Harsh, if you can see some questions, please.
There's some very interesting questions actually.
Please
Did
kindly
I read out, sir?
please.
Yeah.
One by Mr. Bon Neawadi. 3D printing, has that made a difference to your aeroelastic modeling? Has that made it more efficient?
Very, very efficient.
Very
Efficient. Because previously I remember 10, 15 years back, obviously, at least 10 years back, people are using balsa wood, keep cutting, balsa wood. No more cutting. Actually, you just give it on the computer, you come in the morning, everything is done. So it made a big difference. The only thing is it is very tricky though, because you need to compute not just, okay, you have the shape, you can 3D print it, but equally important is what mass that is creating. You need to weigh it immediately, you have to weigh it, not after doing the printing. Even before doing the printing itself, you need to find out what mass this would produce. And then you had to say that, okay, I need more mass. So I had to have brass pieces getting fixed inside my, you know, the shell. Inside the shell, there will be brass pieces to mimic whatever that section is supposed to be creating. So things is a bit more challenging,
Right.
but it helped a lot. 3D printing, amazing.
What about the stiffness?
Oh, the stiffness of the segment won't come. Like I said before, you have gaps.
You get gaps.
That gap is, it is not a continuous shell. Because it is not a continuous shell, it is being attached to the spine system. So when the spine is vibrating, your shell is about 6-inch to 8-inch shells. So it is not continuous, it is not giving any stiffness. Even if it is giving slightest stiffness, you are doing a bench test. Since you are doing a bench test, you already know what frequency is coming and whatever you are anticipating from your SAP model in the computer, whether you are getting that in the model scale or not. So you can easily.
The stiffness is provided by the pipe or whatever.
Spine, only the spine. Yeah,
only the spine.
Yeah, only the spine.
So this is only the covering that you're talking about.
Yes, exactly.
How
the
to
shell.
make the 3D printing is only
Correct. Only the shell. Only the shell. The spine system is
the spine system.
The spine system is basically we give the dimensions to the lathe, and the lathe people exactly cut it the way that we want. So we don't do that in-house. We typically give it outside to cut this, and it will come in pieces, and then we assemble it.
But this is normally in steel, the spine?
Not really. It is either in aluminum or brass. Most of the time, brass or aluminum is being used.
Okay.
Not exactly.
So we hereby admit it's an art and a science, sir. There's no question about it. And the art is in your hands. We may have the science, but the art will always be in your hands with knowledge and wisdom that you've accrued through all those experiences that you've had. That is the key.
Yeah,
absolutely.
The art is on the modeler's hand, I would say.
That's the key
I give due recognition to them because they make wonders in modeling. So, you know, we give numbers, but they are the one essentially making it all work. Actually. So,
yeah, I just wanted to add a point to our audience who are listening. You know, because of the drag on the cable, the diameter of the cable and the Reynolds number is important. And diameter is very important to control of the cables, whether it's cable stayed bridge. Let's take, for example, a cable stayed bridge. The static effect of wind also has to be considered by you. Today, we've been talking about dynamic effects and wind tunnel testing for dynamic effects. But there is that simple thing of static wind effect, which you have to consider. And that static wind effect, because of the cable's drag, the wind it gets dragged on the cable, that builds up the pressure. So a certain percentage of that for, say, when spans are large, the effect of the stay cables providing like a shroud and winding and with its drag will actually have more wind being transferred, more wind load being transferred to the deck and the tower. At say around 800 meters, 700 meters, you will find that the shielding effect of the effect of the wind blockage of the cables with its drag will have a larger static component than the exposed area of the pylon and the deck in itself. So that's how important the long span, even the static wind is critical to consider when you're at very long span.
Yeah, very true. Right. Are there any other questions?
None. By adopting a fish belly shape for a deck structure, Subandhu Pari asks, will there be any, does it affect the inherent damping? The shape, does it affect the inherent damping?
No.
I don't think so.
No.
I don't think so. Because that shape is probably important as far as aerodynamics is concerned, but not exactly on the damping of the structure.
Right. Someone asked, Likon Bishwa asked, please share the presentation. The YouTube link will be kept on the ISTructE website.
Definitely, it will be kept. YouTube link.
Right. Winfred Liwang Eel asks, what is the ideal cable stayed bridge cross section in order to limit the aerodynamic effects?
That's see, that's a tough question. That depends on your B/D ratio, etc., etc. But see, the simple answer to that is you have seen the millimeter duct cross section, because the cross sections are extremely important because they have the nose and they have the incline that the bottom member is inclined something like 72 degrees to the vertical. And that inclination is extremely crucial, you know. So when you make inclination something like 120 degree, 110 degree, the bottom web, it is more bluff and you're expecting a lot of issues out of that.
Yeah.
So one can see it is more like an airfoil shape. You just think about airfoil shape or any streamlined shape. You just look at your bridge deck section. You can immediately recognize whether your deck section is really streamlined or not. You know, as simple as that.
Bringing down the drag.
Yeah.
Yeah.
Okay, the other question being asked is about, please elaborate about the tuning of the tune mass damper. I will just add, Suresh, we had the Helgoland Bridge example presented in one of the lectures earlier, where it's an extremely extreme wind climate and also high rugosity from the surrounding hills, etc., terrain model and all that. And in a construction stage, just at the maximum cantilever of construction stage, they had their 50-year return wind, you know, full wind and storm condition. And in that it withstood, but they had earlier put a tune mass damper at the tip and it calculated its weight and tuned it, and it withstood this extreme event which happened during the construction stage itself. Right. So can you, in the light of that, tell us how this is done, or what are this tune mass damper and its tuning?
Oh, the tuning is basically, there are two things. The tuning is primarily for frequencies, because at that construction stage, whatever is being, whatever the frequency is happening, exactly at the same frequency you need, the damper will be moving at the same frequency. So that is the tuning they are talking about. So the mass is typically, they look at the generalized mass of that particular scenario. And typically the dampers are having 2 to 5% of the generalized mass.
Right.
So, and then the tuning is for the frequency. So it is always out of phase motion with the motion of the bridge.
Right.
So that's the tuning we are talking about. See, the tuning is extremely important, because if it is out of tune, then it is of no use.
Right.
Because bridge will be moving at a particular frequency and the damper is moving at another frequency.
Correct. So getting that mass right is very critical, and also understanding the actual frequency at which the structure would behave.
Correct.
And noting that frequency, and then on that frequency working with your mass of the TMD to work in an opposite fashion to that of the wind-induced motion.
Correct. Yeah.
Right.
Right.
So that is the critical.
Yeah, what we learned was that this mass is put on the deck.
Yes.
And it moves in the opposite direction to which the deck is moving.
Yes.
And that is how it seems to damp the vibration.
Opposite, out of phase motion.
Out of phase. That's what I mean. We do that in buildings. We know.
Yes.
In tall buildings, we put it at the top. But I didn't know that they do it on the bridges also.
Yeah, they do.
Yeah, of course. Construction stage, they will have to. Now come to Likon Biswas, asked two questions. One is how the shape of the cable affect the cable dynamics, the shape and its effect on cable dynamics. And the second is cross ties. How are cross ties anchored with the main cable? How are they connected to the main cables? Two questions.
Well, the first one, the shape is very important, because you are looking at multiple effects. So maybe one type of array may not be very suitable as far as the rain wind induced vibration is concerned. So you are looking at wake galloping, you are looking at multiple effects, incline galloping, and you are looking at rain induced vibration. So you have to pick shapes which is going to be, good for most of these type of excitation mechanisms. Because one should not negate the other one or increase your vibrations and etc. So it's a very tricky affair, but there are a number of literature available, number of studies already done. These are high-end articles one can find out. So there are lots of information already available. So that is one thing. And second question, I do not know exactly how the cross ties are being connecting to the multiple cable. I'm not aware of that.
They have clamps, some special clamps by which they do it.
Yeah. But the point really about that, of course, is that it changes the eigen frequencies of the cables themselves.
Exactly, yeah. It is in place.
That is the key intervention.
Yes.
That is the mode of intervention,
So they don't want it. Actually, it is a big problem for some other reason that you can't inspect the cables, because they have these trolleys which go up on the
cable robot.
stay cables.
Yeah.
And if you start putting these obstacles in between, then there are problems.
Problems to
Yes.
pass.
They don't like it. And of course, the other interesting thing that we were told is that the photograph of the bridge is always taken before
No.
putting the
Crossed eyes.
crossed eyes, so
Yes.
that it looks more beautiful.
Yes.
Then Ankit Panchal asks, while verifying the aeroelastic models in wind tunnel experiments with CFD simulation, what type of turbulence models are used and what is the effect of using different turbulence models? I mean, do we have to use different turbulence models first of all? And of course, then do we mix it with CFD prediction a priori? These are rather the questions.
I can see Suresh smiling.
So we are not using safety at all for these purposes. It is far away from reality right now. So we don't have to even think about that in with respect to aeroelastic. That is even more complicated. Okay,
Yeah.
even simple studies cannot be done. That is the situation. So I don't have not much comments on those directions.
The same question being asked to the panelists, and Kishore Patil asked, what are the softwares available for bridge wind modeling?
Bridge wind modeling, I do not know. Actually, the models that we are using are all inbuilt, in-house built models. We have wind time series simulators. We have 3D buffeting simulators, things like that. So it is all in-house built. It is not like anything that you can purchase. Probably it is out there, which I don't know. So I should not be saying any comments on that. But what we are using is all in-house.
Right.
Actually, RM software is there. It has a module for wind analysis.
Okay.
And there you can do the 3D buffeting analysis. Of course, it
Okay.
requires the input from the wind tunnel with
Right.
respect to your CD, CL, CM
Yes,
coefficient and their derivatives.
Correct, yeah. Correct.
Right.
Thanks, Rich.
Yeah.
Right.
Okay, then Sandeep Patiwar asks, nice presentation, which has made us gone through the complete procedure being adopted for wind tunnel test. Is just a thank you. How do we know the model and the actual bridge have the same response due to wind? I mean, do we correlate them? Is there any verification carried out before and after, confirmation of the design and the measured response?
That is a part of wind tunnel consultants' main job, because this question is a very standard question, because whenever you do wind tunnel modeling, everything is in minuscule scale, 1:200, 1:400. Then you build a building and you put a damper, and how do you know all of these things work? Of course, through full-scale measurements. There are a number of full-scale measurements happening, not only just in buildings, but also in bridges. We ourselves are measuring number of bridges is being monitored. We know exactly what we modeled in the tunnel versus what is happening in reality. In buildings, the famous one is Taipei 101, which has been monitored for the past 20 years or so.
Yes.
And whatever being predicted in 2000, 2001 time in the wind tunnel is being never broken. Okay, those acceleration after many typhoons passed, still that holds true. So that is a confirmation of what we do in the tunnel.
And that has a TMD at the top, right?
TMD at the top, 600 plus tons.
Yeah, at the top.
Many other buildings are being monitored. So wherever the TMD is there, typically it is being monitored because we want to know how the TMD is behaving and how the building is behaving, and means moments of the building in correspondence with the TMD motions and wind velocities, etc.
Right. Actually, there are no more questions.
Okay, so I think it's about time to wind up.
Professor Prem Krishna, you should.
In fact, just a comment on this. How do you make sure that your model results can be are the real, that's a real behavior in practice?
Yes.
In fact, it's a very difficult thing to ensure because in the prototype situation, you can't order windstorms. And you can't order them to the same pattern which you created in the wind tunnel. So
That is true.
I think the only proof of the pudding is that you tested it, you constructed it, and it's standing up safe after 20 years, 30 years. That is the only proof that you have on these things. Also, I think I'm just musing on our deliberations today and all that we have been doing in bridging in the last few months. This year, I have seen a lot of activity on wind engineering and bridges. And it is something which we need to continue with. I think we need to continue this effort. We have now come to a platform from where we can take off, do more activity on this subject. There are lots of issues that have to be looked at. Because I think that in this country, we are going to build scores and scores of bridges in the coming decades. One little example, on the Yangtze River in China, I was told in 1948 they had 3 bridges. That big, long bridge river in China. And in 2009, I was told they had 57. And I don't know, after 2009, they added some. So in almost in that period of 60 years, they added almost 60 bridges, 1 per year. And that's just one river we are talking about. So if we are going to go on expanding our transportation system, communication system, then lots and lots of bridges will come. We need to continue. So I think good time to ask about the 3rd lecture.
Yeah, the topics. The topics and the time frame. Somewhere next month or?
Yes,
not really. Actually, next month I have other lectures coming up.
Right.
And then December also kind of booked. So I think we should push it to Jan.
I think you between Dr. Suresh and the IA structure, you can work out.
The agenda for that, what would be the topics for that, Suresh?
I would say full scale measurements, monitoring, rehabilitation, the importance of those things, and wind monitoring.
Yes, monitoring. Yes.
Yeah, mainly this is the topic that I'm thinking about, because nowadays lots of bridges are aged in many countries. This is one of the area we are working quite a bit nowadays. So probably we can share a lot of stuff which is applicable even in India, because there are a number of bridges which may be getting aged. We can find out how we can improve the situation and things like that. So,
yeah.
Okay.
Probably that's the topic we'll take it up.
Okay. So with that, let me thank Dr. Suresh and his team, Abhilash particularly, who has been in touch with us.
Yeah.
And Professor Tandon, Dr. Harshvardhan, Dr. Lakshmi for joining as panelists, and the IA Structure Office, Vikas Verma, who has been coordinating things. And of course, finally, all the participants who registered and had the patience to listen to us for almost an hour plus. Thank you all for this very, very fruitful activity that you've done today.
Thank you. Thank you all.
Thank you, Suresh.
Thank you. Thank you.
Thank you very much. Thank you.
Thank you.
Okay.
Bye-bye.